Good afternoon and welcome to this session at the 2013 Linux Conference. Our first speaker is Anton Blanchard. Anton works for the IBM Linux Technology Centre. He spends a lot of his time looking for the elusive go fast bit for customers in various states of panic, from embedded devices right up to supercomputers. No problem, too small or too big. Thanks, Anton.
Thanks, Steve. So who thinks systems are getting more and more complicated and harder to debug and analyse? All of us, I think. And the tools really aren't catching up, keeping up with what we have to debug. Often the challenge now is to really decompose a problem between so many different levels, and the levels are only increasing. We do the application, the compiler, the middleware layer. Now we've got hypervisors, we've got more and more firmware layers. And then we've got the obvious ones of CPU, memory, and I/O. So things are definitely getting more and more complicated. So what I thought today is run through some of the tools that I use, some of the processes I use for debugging performance problems, just to show and hopefully educate some of us on some maybe better ways of analysing things. I think performance is something you always continue to learn. I'm still learning. I still make a lot of mistakes. So I'll start. We'll start simple with some simple tools, and then we'll build up into the more complex ones. So if you had a performance problem, what would be your go-to tool? What do you think you'd attack with? D-Trace. We won't be talking about D-Trace. Anything else? Top's a good one. HTOP, great. That's another great tool too. S-Trace, yes, love S-Trace. A lot of those. All of the above. Perf. No one's mentioned Perf Events, the Swiss Army knife of Linux. Debugging and performance analysis. Profiler, yeah, a bunch of tools. What's that?
Format and profiler.
What's that?
It's great. It's shell script that just only has GDB run backtracing the process and aggregates.
I love that, yes.
Format and profiler, it actually works, unlike GPerf, it actually works.
Yep, and the advantage there is you get full dwarf-based debug backtracing too, which with something like Perf you don't always get. So yeah, I've definitely used that in anger.
Stalls on production database servers.
Especially, I guess, a threaded one if you have to stop all of them. And yeah. But a great idea too, yeah. So we'll start simple. The first tool I might tend to use is Uptime. And it tells you the number of processes that are running, ready to run, or blocked on I/O. Gives you a bit of an idea where it is. Rule number 1, 13,000, probably a little bit high. That was a machine we had in our test. The test teams at IBM really take their job seriously, and they love breaking our stuff. So, you know, with great honour that they come along and say, we've got a performance problem, the machine's almost dead, fix it. Running Uptime's lightweight. With a lot of these performance problems, you'll find if you start using the more heavyweight tools, even things like Top, we often have situations where we log into a machine and Top takes 30 minutes to display something. So obviously something wrong there, but at 30 minutes at a refresh rate isn't really going to give you anything useful. dmessage, back in the old days when we all used to sit there and type in our consoles, we'd always look at dmessage. Well, the console print key buffer would spam us in the face these days with X and remote machines. Not a lot of people look at it, and a lot of the time that's the first place you should check, obviously. Simple stuff, but we often forget to. The catch, or kind of the canary in the coal mine for a lot of bugs we have these days, is basically when we get something like this I/O stall, and it isn't necessarily an I/O problem, it could be something else. But again, that's something to check for, and it's something you can then use to analyse what's going on. VMstat, the next one, someone mentioned VMstat. Very lightweight. Interesting story behind that tool, actually, because it used to be somewhat more heavyweight, and there was this ancient benchmark from Spec called STET, and it was terrible benchmark, but it was basically a terminal user benchmark, so all these people at universities were sitting there typing on their terminals, and I guess when it stops responding, everyone starts typing VMstat, and so it's part of the benchmark. And so, part of the benchmark, our job is to make benchmarks go faster, so we made VMstat go faster. So it turns out that now VMstat, I think, only loads maybe a couple files in proc. It's pretty much guaranteed to run. Another lightweight and good tool to use. Little plug for DStat. I like DStat. It's a tool that basically amalgamates a bunch of different information. You get the complete breakdown of all your different levels of where time is being spent. Most people, there's a bunch of kernel people who this is second complete knowledge to them, but for people that aren't, Obviously, you spend time in user space. You can spend time in the system, in the kernel, doing something. If you've got nothing to do, you're in idle time. And then you've also got wait time. Wait time is a pretty awful metric because the absence of wait time doesn't mean you don't have an I/O problem. You can easily have something that's CPU bound but also has I/O problems and it won't show up as wait time. But if you do see wait time, then it is a good sign that there's something you're blocking on I/O and there's something maybe you need to look at. Dave's smiling. There's no heckling there yet.
Do you want me to heckle?
No, that's fine. Save it till later. And then we get into like hard IQ and soft IQ. So hard IQ is usually the first part of an interrupt handler, and its job is basically to do its work and get the hell out of there, and then it might hand off to a soft IQ. So you get a nice breakdown there, and then a bunch of other stats. So like this is like a quick dashboard, and you can kind of see how the machine's performing. We mentioned top. Top's great. Hit 1, you get this nice per CPU profile, very useful. As I said, prone to hacking, prone to hanging. And someone mentioned HTOP, another great tool there, and that's just it running here in a box, and you've got, again, the breakdown. We'll talk a bit about stolen time as well. When we add hypervisors, we've got yet another level of time we keep, and that's called stolen time. But here you'll see, every CPU broken down. With a lot of performance problems, if you look at the aggregates, if you look at the system-wide stats, it really won't tell you what's going on. In a lot of cases, it's a single CPU that might be blocking. So these kind of stats are useful because you can go in and potentially see one guy that's in trouble, and then you can drill down on that. Someone mentioned strace, another great tool. There is some interesting things going on. Acme is working on some interesting things around perf trace that I might mention a bit later. But this is installed everywhere and very useful for looking at latencies when tasks block. And it's a bit of a contrived example of Sleep 1. Looks like a contrived example, but we actually had an application a number of years ago that was taking forever to run, and we looked into it, and eventually some programmer put a Sleep 1 in the middle of the core loop for unknown reasons. So, a bit crazy, but it's actually a real problem we found. Let's talk about perf a bit. So perf's really kind of the, I guess, the Swiss Army knife of Linux performance analysis now. So a lot of the stuff that goes into Linux to do performance analysis ends up in perf. And I could talk for hours, but I won't on perf. I don't have the time. But we'll look at some of the best bits of perf, I guess. What I think are the best bits of perf anyway. You may not necessarily agree. Perf stat's probably the easiest place to start. So perf stat is just a way of getting performance statistics, and it's both kernel statistics, it's also performance monitor statistics off the hardware, so you can basically drill down in either direction. The operating system ones, you can look at things like how much CPU time have I used, how many context switches have I had, how many page faults have I had, all that kind of interesting statistics. And then the hardware PMU stuff is application or hardware CPU specific, but there's a wealth of often hundreds of these different events. At the moment, unfortunately, there's only a small section of kind of generic events where you can actually specify an event across CPUs, perhaps say a translation miss or a cache miss or something like that. There's a lot of people working on improving that, maybe adding more events. The other trick will be to actually have the per CPU specific events as well, because eventually it's somewhere where we really let down here compared to most other commercial profiling products, and even some of the old ones like OProfile, where you actually have the easy ability to use a symbolic name for a translation miss or a pipeline stall or something like that. The thing that lets us get away with it at the moment, you can actually specify raw events. So if you actually know what the raw event is, you can program that guy in and profile on it. What I tend to use is libpfm out of the perfmon2 suite, I guess, has a set of tools you can use to take your CPU and look up events and stuff like that. So that's quite useful when you need to drill down. Simple example, just kind of scaling an array here. Looks pretty boring. We allocate it statically, so it's in the BSS, and we walk through it. And potentially now we're going to look at this from a perf perspective. We're just running perf stat without any parameters at the moment. These are at the moment the set of events that we've decided to display by default. And you start from the top and it's reasonable, hardly any context switches, hardly any page faults, looks pretty reasonable. And you come down to instructions per cycle, and 0.02 is horrid. I mean, that's shocking, I guess, especially with modern CPUs where you're talking superscalar out of order with a good algorithm. You're hoping to be around 1, maybe hoping to be above 1, 2, 3. But if you're down at 0.02, you've got real problems. That's not always the case. I mean, you could have algorithms that are maybe pointer chasers, and basically then you're limited by how long it takes you to get out to memory and back. Too bad. But in a lot of cases, you can kind of get a feel and see what the IPC is doing, and you've got issues. You've got some ability to improve it there. And then it's taken us about 38 seconds, so it's given us a good idea of what's going on. We can drill down, and this is some of the generic events that perfstat has. And so we have generic translation miss counts and cache miss counts, and they should work across CPUs. This is done on a power machine, but it'll work on, say, an x86 box as well. Sky high, so we've got problems everywhere here. So we're taking huge numbers of cache misses and huge numbers of translation misses. Again, there's something probably wrong with our loop here. Time to investigate. So it turns out we're accessing the array in the wrong direction. Instead of accessing it row first, we're accessing it column first. And the issue is, we can take a step back and talk a little bit about caches. Caches have cache lines, and they're a specific chunk. They might be, say, 64 bytes, they might be 128 bytes, and you pull that whole cache line in when you want to look at data. So if you pull a cache line in, you really want to use the rest of the data instead of throwing it away. If you have your array the wrong way, you basically pull out a piece of information from each cache line and then roll around and do it again. Very inefficient. So in swapping that around, it's gone from 38 seconds to 0.8 seconds or 0.79. Big difference. And the IPC now, I'm much more happy with this IPC. I think that's looking pretty good. So you might think, interesting, but that's really a rookie mistake. No one should make a mistake like that. We'll talk a little bit about Spec CPU. It's kind of an interesting aside. This is Spec CPU 2000s. This was a long time ago. But there was one vendor that got a massive improvement on one of the workloads inside Spec CPU from a compiler change. And whenever that happens, the industry's kind of a bit suspicious. What's going on here? Have they broken the benchmark? What are they doing? And it was kind of a fascinating set of circumstances so it turned out that same problem was happening in this benchmark art. So it was a two-dimensional array, and it was being accessed with a bad footprint, or in a bad way. So these are the tricks they did. This is kind of like fascinating from my perspective, and I'm not a compiler guy, but some of the heroic things that go on just for benchmarks, it's kind of interesting. So the first thing is, it was a two-dimensional array allocated dynamically, and in C you might do that by allocating the first dimension, set of pointers on the first dimension, and then malloc-ing the second dimension. The first trick is that you have to look at that allocation and decide, I'm going to take all those mallocs and I'm going to replace it by one malloc, and then allocate the array differently. And already that's pretty incredible stuff, because C's great, all these pointers and everything, so you've got to do an analysis, an escape analysis, to make sure that no one else is looking at that array. That's only the first step. The second step is then you've got to sit back and look at the array and decide, well, I'm actually accessing it backwards, so I've got to swap it. You might use feedback optimization, or you might use kind of loop heuristics and stuff like that. And even then, that wasn't enough. The third trick was that you took a composite structure and you broke it down, because it turned out instead of accessing every field in the structure, you'd access one member. So instead of having this struct, you split it up so that you walk through it in a more compact way. Pretty crazy set of improvements. In fact, we got great research guys. They actually implemented all of this in GCC, and we got a 5x improvement in art, which is pretty crazy. Unfortunately, it's just gone out recently, I heard, because of issues with link time optimizations. But the link time optimizations, the global optimizer, and all that kind of stuff. And I guess my next rule then is, if you want the entire hardware and compiler industry to tune your application, just get it into Spec CPU. So we'll keep moving on in Perf. As I said, I love Perf. Great set of tools. The next one I'd like to talk about is Perf Record. This Perf Record, archive, report, and annotate kind of cycle. And this is where you're doing exception-based profiling. You're taking addresses and you're taking backtraces and producing a set of functions, that top hitters and stuff like that. Record is the one that you use to record, so you give it events and it produces an output file. You can use perf archive, which is very useful for embedded systems, so that aims to basically look at the profile data and then suck in all of the shared libraries, executables, all that kind of stuff. And it's, in theory, should work across architectures, 32, 64-bit, big, and little endian. It's an interesting, I'll give you a plug for, I don't know if Ben's here, Ben's got to talk in endian tomorrow. It's something that everyone gets wrong. We got it wrong again in perf. The mistake was made a long time ago in Linux, and it was kind of repeated inside the perf ABI format, so it's a little disappointing. I think it tries like 4 or 6 ways of trying to work out which exact endianness and bit size you are before it gives up. Perf report is the analysis phase, so we'll show a quick perf report and give you an example there. And then perf annotate is when you drill down and you might do assembly and source level debugging. So here's a bit of a profile output from a problem we were looking at recently. It was basically a copy on write page fault benchmark. So well, this is a benchmark I wrote based on something we were seeing in a customer workload. So it's just a simple test case. The first step is get a test case that's representative, and then analyze it. And you can see here the top one with a huge percentage of 67% is our copy page routine. So there's probably something we can do there to optimize copy page. Seems like it's the first place we should go. And one of the great things I find out of perf is that you have these great backtraces, which second only to, as Stuart was saying, using GDB to backtrace. It's probably the best tool you can get. It does rely on a lot of things in terms of frame pointers. There's some tricks going on to be able to dump entire parts of the stack and backtrace it. It's somewhat of a difficult problem because we actually do the backtraces in the kernel, so we really don't want a full dwarf-based backtrace engine in the kernel, I think. And then the patch. A lot of the time, once you work out where it is, the patch, I was going to say write itself. It doesn't quite write itself, but it's usually obvious what you have to do, and there we managed to bring it up by about 17% with a change to copy page. So we added some special prefetch instructions and a few other things. So once we knew what the problem was, off we go and fix it. Next one I want to talk about is all the in-kernel tracing. There's a lot of in-kernel tracing that's quite useful. It all lives in debugfs, which is becoming maybe a bit of a dumping ground for stuff, but it's in there. One of them is kernel trace points. So there's the ability to have these lightweight trace points and they are actually quite lightweight now with some of the new stuff that has gone in recently. When they're not enabled, they're quite lightweight. When they're on, they can be extremely heavyweight. And they're added by kernel developers. Someone decides this is a good place to put a trace point. Dave might decide an XFS, he needs one here, so that goes in, and then basically anyone can exercise it and anyone can use it. System calls as well, so you could trace system calls through that if you wanted to. The other one is ftrace. Ftrace is a bunch of traces. The immediate one that I think of that's quite useful is the function tracer. That isn't enabled by default because it's somewhat of a heavyweight trace function, but it allows you basically to get an in-kernel trace function by function in and out. So for someone who doesn't really understand how the kernel works maybe, or doesn't understand where the performance problem is, you can turn that on, basically look through the trace, and it'll tell you which functions you're bouncing through, gives you a good idea of how the kernel is operating, what it's doing. Here I've just used a context switch trace point, just as an example. You can use them directly in sysfs. Perf also has a wrapper around it, so you can use perf to enable these and dump them and all that kind of stuff. And here we're just seeing, looks like bash is context switching in and out with a kernel work thread. So just a simple example. They're very easy to make. So if you have a driver or something like that and you think you want to sprinkle it with debug print keys, another option is create some trace points that you can enable when you need to. You could say it's a little bit cleaner. The other trick is sometimes you can also link to them in kernel modules. So if you decide you want to build something that traces and analyzes and all that kind of stuff, and you can only do it in the kernel, you can actually link to the trace points, which we've done in the past. That's the function graph. So this is just a system read from a pipe, simple stuff, but it gives you all the functions you've gone through as you call. So the system call as you enter, right through to checking to see if the area of memory is clear, or from a security point of view, if you should be able to write to that area of memory. And then you do the pipe read, and there's a lock and unlock. So basically, you've already got your complete path through the kernel, which is nice to see. QEMU is another great tool because then you can trace all the way through user space and kernel and get a full assembly, disassembly. We use that quite a lot as well. Love LD preload. I think Stuart might have been talking about libeat my data. I heard yesterday, which is it an LD preload hack or?
Yeah.
Love it. Yep. You do anything with LD preload within reason, and we've been known to. It's especially good with applications that maybe you don't have the source to at the time, or it's just difficult to rebuild. You can just add this shim in and pretty much do anything, confuse, hide from the application, anything you want to. This was in my junk code directory. We had an application years ago that just had an arbitrary limit on the number of processes. No reason at all. We bring up a new machine and it had 1,024 threads, and this thing would just not run. It's like, well, what the hell's going on? And it was obvious it was calling syscomp and then barfing out after it. So the trick is you can just lay yourself between syscomp, simple stuff. So you can link into the next guy. So you link back into syscomp in the library, but just intercept it. So if we ask for the number of processes, we just get it from an environment variable, and we can keep going. Love LD preload. Last one, when all else fails, nothing else is working, the machine's catatonic, you're in trouble. What are we going to do? Well, this is really the last-ditch effort. Unfortunately, sysrec isn't enabled because it's really a bit of a security risk. If you just had random machines enabling all the sysrec ability, you can do a bunch of things. You can kill tasks and all this kind of stuff. But if you are fighting a very nasty problem, it's a good way to try and get an idea of what's going on if you can't log into it. And this one here is a machine backtrace I found from somewhere. It's pretty obvious we've got problems. We're trying to execute a process. PMD we're allocating a page table entry in the MMU code. And then we block. Obviously, the memory isn't available. We're in D state. You look at this and think, okay, we're in trouble. We don't have enough memory. It's basically the problem. So it at least allows you to kind of get a last-ditch effort to try and understand what the hell is going on. More miscellaneous tools. PerfScript is kind of an interesting one. It's the ability to use Python and Perl-based scripts inside of Perf, which is quite powerful. So there's a bunch of maybe 15 to 20 different perf scripts at the moment for doing various things. One of them's system call top, so you can just like top, but it'll show you system call numbers per second. There's other ones to do per process read and write, breakdowns, all that kind of stuff. Perf lock, if you think you've got a kernel locking problem, perf lock is what you want to use. Perf trace is the one I was talking about earlier that in theory will allow you to produce a lot of the same metrics that something like strace provides, and potentially a lot lighter weight too, because it's all happening in kernel. The ptrace interface is pretty damn inefficient that strace uses. A bunch of block tools. Jens Expo's got his block trace. So you can basically, if you think you've got an IO scheduler issue, you can trace what's happening in the kernel in terms of IO. And that was, I was going to say recently, but a while ago, ported on top of trace points. So he's using that generic trace points functionality to provide that block trace tool. A bunch of networking tools, the usual netstat, TCP dump, Wireshark, et cetera. Stuart mentioned GDB, love GDB, and we've used that in Anger a number of times, definitely. LSO, Veltrace, do a lot of binary patching, especially. We had a litany of applications that decided they wanted to look at proc CPU info and look at the number of CPUs, and again, more than 64, can't handle it, I'm out of here. So binary patch that string to temp CPU info underscore or something like that. Put your own CPU info in. It's just easier than modifying the kernel, right? Task set and NUMA control. It's always good to try and drag the program back to something more simple and easier to understand. In a lot of cases with workloads that are bouncing around, it might be hard to see exactly what's going on. You can lock those guys down to a particular core, a particular thread, make the problem a bit simpler. Finally, load generators. Again, Jens has got a tool, FIO, which is great for basically having a repeatable way of replaying workloads, I/O workloads, so that if you're trying to analyse a problem, you've got a way to produce that I/O. And Tridge has got some great tiny little tools called sock sync and sock source, which is just for doing like a TCP kind of socket, and it's much simpler than a lot of the other benchmarks. So you basically just get down to socket here, socket there, data comes across, where's my problem. Second diversion. In my years at IBM, I get a lot of weird bug reports. This was probably one of the weirdest, one of the most interesting tools that I've seen used. They had a compute benchmark, and it was basically running compute benchmark on one core, and they came to me and said, there's a Linux scheduler problem, you got to fix it. And I didn't exactly say prove it, but I said prove it. And they sent me this output, and they said, we're pretty sure it's a problem at your end, please fix. What it actually was a thermal map of a CPU. And they sent me that, and they said, something is moving on that chip. Please fix. So yeah, it's basically an XY map of a thermal map of what's happening on a multi-core chip. And so obviously we've got a problem. This compute benchmark is bouncing around where you'd hope it was sitting in one spot. So that was pretty interesting. This is where things kind of get messy, because up until now, it's been fairly easy to isolate a problem and try and work out what's going on. Unfortunately, these application guys are conspiring to make life more and more difficult for us. So Java makes life quite difficult. You no longer have this static mapping of an instruction address to an opcode to an instruction. Because obviously it's just-in-time compiled. So you have to have a way of linking, of providing the information at runtime. The open source JVMs have a much better way of doing this, but if you're working with some of the vendor ones, for example, the IBM one, you actually link in a shared library to the JVM. It's pretty horrid stuff. And so I got a quick thing there just to link it in, to create that object file for perf so that you can do at least function level profiling. The other issue is things like garbage collection. So garbage collection can get quite nasty. You can talk to Paul probably for hours about all the real-time issues with Java garbage collection. But it's consuming a lot of CPU. It also creates stalls. We find a lot of performance problems there. It can be quite difficult to understand. At least then, if you're using something like perf record, you can actually usually see what's the functions in the JVM that are garbage collecting. So you kind of have an idea. If you're spending 40% of your time garbage collecting, it's probably something you need to tweak. There's probably an issue you need to fix. But if you're spending 5%, you're probably okay. The other part where it gets quite difficult is interpreted languages. So this is, I think, an area of weakness generally with our tools. Some of the scripting languages, Python and Perl, have their own profilers. Not too bad, but when it comes to doing higher level profiling, say with something like perf's not going to give you anything useful, unfortunately. Things also make it worse. We spent some time, a number of us spent some time looking at OpenStack recently, and it was very difficult to debug and understand. I'll just say that. It uses user space coroutines, and back 10, 12 years ago, all the rage in pthreads threading libraries was this M2N model. So you'd have M kernel threads and N user space threads, and you have a user space scheduler. That's really a road to madness. It's just so difficult to understand, so difficult to look at it from a high-level perspective, a profiling tool, and know what's going on. None of the user space context switches really get surfaced up to the tools. So when you start adding these user space coroutine and threading things get really difficult. The other one is hypervisors, and this is another area that's becoming incredibly difficult to debug. I mentioned stolen time, so we had user, system, idle, soft IRQ, hard IRQ, nice. We added stolen, so we've got what, 7. Stolen is basically the time you should have had that the hypervisor took away from you. So you need a metric to know that I didn't actually get all the time I was given, that's stolen time. And it gets really difficult now because you've got stacked schedulers. So all of a sudden you've got a scheduler on top of a scheduler, and you do things potentially in user space and the guest kernel that may not behave as well. One word for it is multi-tiered locking. Some locking primitives, I see this a lot in big applications, I won't mention any names, but they decide that they're better at locking than the kernel, so they actually have this multi-tier locking. They decide that we'll spin for a while, then we'll try for a while, and then finally we'll call a blocking primitive. So that's kind of multi-tier locking. When you're X levels deep and you're busy looping for another CPU that isn't necessarily even running, you're just wasting your time. So we see a lot of this kind of stuff, and it just gets worse with hypervisors now because you've got 2 levels of this going. The other one, an interesting one, is turbo mode. A lot of the vendors now have turbo mode. Things go faster sometimes, so they don't sit at nominal frequency. They might be a 3.2 gig CPU, but they might burst higher than that. How do you expose this? We don't really have any good ways of exposing it. A lot of the tools aren't happy at all if you burst above 100. What does it even mean? But what's the opposite? Do you make nominal like 90%? Then you get complaints from people saying, I'm not using all my CPU. So it's one of those things where the tools aren't great and there's no real good answer. Threading makes it even more difficult. So we call it simultaneous multi-threading, Intel call it hyper-threading, but the ability for one CPU core to have multiple threads of execution, all of a sudden then run-to-run repeatability could go out the window because you could have something random on another thread on the same core. It might run twice as fast one time and twice as slow the next time. And what we tend to do is trying to lock that problem down, just look at it from a single thread perspective. Talking about this multi-tiered locking, if you look at anything like this, the first thing you notice is that these applications are just pounding on this thing called sched yield, and it's a horrible thing. Never use sched yield. If you ever think it's a good idea, it's not. Don't use it. But we find with these applications that they'll tend to use sched yield in this area where they're kind of busy looping. They haven't quite decided that they want to block and stop, so they're going to sched yield for a while. And what happens is from scheduler to scheduler version, someone tweaks something tiny, and the whole way that sched yield kind of operates changes, and these benchmarks or workloads vary wildly, so avoid it. The other trick is if you see kernel futex issues, even if you see a bunch of time in the kernel, it's often actually not a kernel futex issue. It's often not a kernel issue. It's not even often a pthread library issue. It's usually maybe a locking issue in the application. And we've got tools like perfscript futex contention to kind of try and drill on that. The final one here is watch out for negative scaling. Working for a hardware vendor, we always like to sell more hardware, but it's a bit embarrassing if you sell more hardware and the performance drops. So you really want to know that what you're operating in a positive scaling area and you understand the problem, and that throwing more hardware at the problem is actually going to help and not hinder things. So I thought I'd finish maybe with a top 10 performance mistakes. Maybe not the top 10, but the top 10 I could think of at the time. First is not having a representative test case, obviously. So the first step is that you need something that represents reality. I shouldn't say always, I have been guilty of this in the past as well. So I get a cut down test case from a customer or something, look at it and say, oh, I know exactly what that is, go off and fix it, kernel patch, get it merged, and the vendor tries it, does nothing. Wasted my time. The second step is obviously completing that analysis. So even if you do have the right test case, you may not understand why it's failing. So what you want to do is go in and analyze it first. Let's just throw more hardware at the problem. Doesn't always work. In fact, often with some workloads, less hardware performs better. Our algorithm is better than the obvious one. Radio had a comment yesterday saying that she wished more people in the industry hated computers. I wish more people in the industry feared complexity. I think in a lot of cases, a lot of people like to do complex things that aren't always the right idea, may have corner cases that people don't understand and break down in awful and horrible ways. So if you are looking at something and replacing the algorithm with something different, more complex, not as common, really take a step back and understand if you should, if it is giving the performance improvements you want and the trade-off does make sense. Let's just put it in user space. I see Stephen here. There's always a rush. The kernel's difficult or the kernel's slow. Let's get it in user space. In Stephen's talk, he talked a bit about where you want to be operating in terms of, say, packets per second and packet size. If you're not in that bleeding edge, stay away from those things. Again, road to madness. Let's just put it in the kernel. That's the other problem. You have something in user space that really doesn't have any performance issues. Who really cares? Maybe a random USB drive or something like that. It doesn't need to go in the kernel. We don't need to make it go faster. Writing your own malloc library. Thankfully, this doesn't happen as much as it used to. glibc for a while wasn't accepting maybe as many malloc patches, performance improvements as it should have. Things like pooled allocators and stuff. So it really had some big issues with threading. It's got better recently, so not as many people do that. But if you're thinking of doing it, again, bad idea. Go write a window manager or something instead. Doing your own locking. That's the other one. Everyone thinks locking isn't, how hard could it be? I'll just write my own. They always get it wrong. I mean, that's just, again, you will make a mistake and it will bite you at the worst time. It'll be an awful to debug issue, or it'll fail in production or something like that. There's plenty of things. I mean, there's glibc built-ins, there's pthreads locking, pthread libraries, obviously, all of the primitives in pthreads, locking libraries, whatever. Stay away from writing your own locking, especially if it's got pthread, if it's got a sched yield or something, those kind of things. Stay away. Benchmark-specific hacks, another one, we tempt to stay away from, but sometimes creep in. And finally, again, the answer is never. We need more sched yield. So with that, any questions?